Hello, and welcome to another video for Astronomy 102. Today our topic is light and color. As Kate discussed in the previous lecture, light is absolutely essential for astronomy. Astronomy is a peculiar science in that we study things that are so far away that we can never hope to interact with them directly. The scales of the universe are so vast that even to get to the very nearest star would take 4 years traveling at the speed of light. And remember, light is super speedy. It can go around the Earth 10 times in 1 second. The Voyager missions are now exiting the solar system at a respectable speed of 38,000 miles per hour. At this speed, you could be in Phoenix in about 9 seconds, which would make trips to IKEA a lot less painful. But even at these speeds, Voyager would take more than 70,000 years to get to the nearest star. That's a long time. 70,000 years, our ancestors were still figuring out rock tools like these. So you get it, things are far. This means we can't collect gas from stars and analyze it in the lab like a biologist might. We can't take a sample from one star and compare it to another as a geologist. And we can't smash star stuff into each other to see what happens like a wacky particle physicist. And yet, we study and attempt to understand the processes inside nebulae like these that are thousands of light years away, where stars are forming. We can study supernovae to understand how and why they explode the way they do. And in my own research, for example, I can study the most massive objects in the universe, galaxy clusters, which are more than 2 billion light years away. Incidentally, galaxy clusters are particularly cool because they can magnify objects in the background. If you squint closely, you'll see that surrounding this the center of this cluster in every direction are these tangential arcs. I'll zoom in. All of these arcs that you see are background galaxies that are being lensed by the mass in the galaxy cluster. Some of those background galaxies are all the way in the other side of the universe, more than 10 billion light years away. The only way we have to gather information about these things is by analyzing the light they emit. Given this fact, it's amazing that we can know anything at all about the universe, given that pretty much all we can do is sit on our planet and wait for the light these objects emit to come and reach us, and catch it and analyze it when it does. So given that pretty much everything we know about the universe we know by analyzing the light that comes from it, we naturally have a few questions we need to answer about light before we can proceed. Here's a preview of what we'll be talking about in the next few lectures. We will begin today by asking, first of all, what is it? What is light? It's a surprisingly complicated question. We'll have to look at how light behaves and interacts with matter to understand what it is. We'll want to understand how light is transmitted, how it travels, and how it interacts with things along its path. What happens to light as it travels across the universe? When I look up at the sky at night and observe a twinkling star, I know that the light that I see has been traveling for years, tens, thousands, sometimes hundreds of thousands of years. The light travels from that distant star somewhere in our galaxy until it finally encounters my eyeball, where it is absorbed by the back of my retina, and this creates a signal that is transmitted up to my brain and makes me think, oh, there's a star in the sky. In this lecture, we'll take a quick detour into human vision to understand how we, as human beings, perceive light. In the end, though, your eyeballs are not very precise measuring instruments, and they are also very small. In the next lecture, we'll talk about more efficient ways astronomers collect light from objects that are trillions of miles away, and the types of devices they use to analyze the light they collect. We'll also need to know more about how light in these astronomical objects is generated. What types of physical processes create light? Why does a light bulb shine when you plug it into a socket? Why does the sun shine, and why has it been shining so steadily for 5 billion years? These questions we will cover next week. Finally, we'll spend a little time investigating the different ways light interacts with individual atoms. As you'll see, these types of interactions are very common throughout the universe and can tell us a whole lot about what the universe, its stars, and galaxies and planets are made of. So, what is light? In 1666, the father of modern physics, Isaac Newton, sat in his study at Woolsthorpe Manor pondering just such a question. Forced out of Cambridge University by the threat of an advancing plague that would sweep the nation and kill over 75,000 people, he retreated to his childhood home, and there spent a fantastically productive year, during which he would tackle, and solve, many problems of optics, mechanics, gravitation, and calculus. It was at Woolsthorpe that Newton reportedly observed, or according to some accounts was hit on the head by, an apple falling from its tree, and was struck by the idea of universal gravitation. When Newton was not contemplating his orchard and the fruit within it, he spent a lot of time wondering about light, colors, and their composition. With a simple prism, he proved that white light was in fact composed of many different colors, a so-called spectrum. And furthermore, that once a color had been extracted from the white light through a prism, it could not be split further by another prism, but remained pure. The prism is said to refract the light and decompose it into individual colors, or more accurately, wavelengths of light. Monochromatic light is pure light, light that has only one wavelength or one color. In his spectrum, Newton thought he could identify 7 pure colors, and he devised a color circle where he related these to notes on a diatonic scale and the 7 known planets at the time. Despite all his scientific achievements, Newton was still a bit of a mysticist. In fact, we now know that a prism disperses white light into an infinity of wavelengths, a continuous spectrum, in which there are no separate colors, but just a continuous gradation from red to violet. Newton aimed his decomposed light at different objects, and he concluded that the reason, for example, an apple is red, or any object is red, is that when you illuminate it with white light, you're actually illuminating it with all these different types of light. And the apple is absorbing pretty much all of them except for red light, which it reflects. And so you see a red apple. If you shine monochromatic green light on a red apple, it'll be pretty nearly invisible, because it absorbs almost all of the incident green light. Newton added these observations to his new theory of colors and concluded that color is a property of light and not of the object itself. When Newton examined the dispersed spectrum closely, however, he noticed that some naturally occurring colors were absent, such as brown or pink. This led him to the conclusion that color must not be an intrinsic property of light, after all, but is instead a quality that is manipulated and maybe even defined by the observer. He therefore abandoned his prisms and his slits, and he turned his experiments on himself, determined to understand the human role in the theory of colors. According to his journals, he probed his sense of vision by sticking needles in his eye socket between eyeball and bone, and in his own words, pressed my eye with the end of it so as to make the curvature in my eye. There appeared several white, dark, and colored circles. He concluded the colors were a function of how much pressure he applied to the back of his eye. And please don't try this at home, kids. On another occasion, he looked at the sun for as long as he could bear, and spent the next few days in a dark room until his eyesight recovered. 200 years later, Thomas Young, in an amazingly prescient work, proposed that the entire range of human color perception could be achieved by combining 3 monochromatic colors in varying degrees of intensity. He said, as it is almost impossible to conceive each sensitive point of the retina to contain an infinite number of particles, each capable of vibrating in perfect unison with every possible undulation, it becomes necessary to suppose the number limited, for instance, to the 3 principal colors, red, yellow, and blue, and that each of the particles is capable of being put in motion more or less forcibly by undulations differing less or more from perfect unison. Each sensitive filament of the nerve may consist of 3 portions, one for each principal color. Thomas Young was a proponent of the wave explanation for light, and he understood it to have an infinite number of wavelengths. And what he meant was that he could not understand how our small retinas could have receptors that would be completely tuned to each one of those infinite wavelengths, and so that our receptors would have to be capable of absorbing a range of wavelengths. And once you accept that point, that they can absorb a range of wavelengths, then really you only need 3 different types of receptors in order to form every color distinguishable by man. In fact, just a few decades later, the first images of retinas with microscopic dissections were performed, and they confirmed the existence of 3 types of photoreceptor cells, which we call cones in the eyes. They are sensitive to long, medium, and short wavelengths of the visible spectrum. We also see these long rods on the left-hand side that are more sensitive and can detect lower levels of light, but that don't discriminate between wavelengths since there's only one type of rod. Incidentally, if you've ever been to a star party or hung out with an astronomer anywhere near a telescope, you may have been told to use your averted vision when trying to see very faint objects. The idea here is that you avert your eyes a little to the side, and the object that you're trying to see that's very faint will become a little brighter. We can understand why by looking at this graph on the bottom right that shows the distribution of rods and cones as a function of the distance, in this case the perimetric angle, from the center of your retina. You see that at the very center of the retina, or at perimetric angle 0, there's a huge peak of cones. The number of cones per millimeter squared is much higher right at the center. That's where your color vision is the best, is when you're looking at something that's in the center of your field of view. But now look at the distribution of the rods, those much more sensitive receptors that we use in low light situations. Those rods, the distribution of the rods, peaks about 20 degrees off of 0, so 20 degrees away from the center of your retina. And that again is why, if you look a little bit to the side, you'll be able to use the rods in your retina to look at that faint object, and it'll become brighter. If we look at the cones now, you see in this picture of a human retina, there are 3 different types of cones. There are some cones that are very sensitive to the blue region of the spectrum, cones that are sensitive to the green region of the spectrum, and cones that are sensitive to the red region of the spectrum. Each cone essentially acts as a collecting bucket, and it counts the photons it receives in a specific wavelength range. It's a little bit more complicated than that, in that they aren't perfect buckets in the sense that they don't perfectly count every photon that arrives between one wavelength and another, but rather their ability to absorb photons depends on the wavelength. And for the blue cones, it peaks in the blue region of the spectrum. For the green cones, it peaks in the green region of the spectrum. And for the red cones, it peaks in the orange-yellow region of the spectrum. In the dashed line, we also see the sensitivity of the rods. So again, rods aren't able to discriminate between different colors because there's only one type of rod. But the rods themselves are more sensitive and are able to absorb more of the blue photons than they are of any other, the blue-green photons, I should say, more than the yellow or the red photons. In fact, you can see from this figure how bad human eyeballs are at detecting really red light. So anything that's higher than 650 nanometers or so, the eyes have a really hard time absorbing that light. And that's the reason why when you're out trying to look at very faint objects, for example, during an observation or a star party, we suggest that you use red flashlights. It's because your eyes just aren't very sensitive to red, and so it's a faint color to it. They don't see it very well. So after a certain period of time, the brain will tally up the number of photons absorbed by the blue cones and the green cones and the red cones, and it'll say, okay, I have 20 red photons, I have 10 green photons, and I have no blue photons. So that means that whatever I'm looking at must be brown. And the brain essentially does this arithmetic all the time for all the things that are in our field of view. And with just these three numbers, the brain can come up with the whole color or hue range that human beings are able to see. So with just three colors, three numbers, you can literally make every color known to man. So color as we perceive it is really a construct of our brains. In reality, there is an infinite variety of colors or wavelengths of light that we can't distinguish between, at least with our eyes. But again, what is light? Newton struggled with this question his whole life, as well as many other distinguished scientists of his and later generations all the way until the middle of the 20th century. A way to try to understand what it is to look at how it behaves. Light often behaves like a massless particle, a photon. It travels in a straight line unless it interacts with something else. It travels in discrete packages or units, which we call photons, and these can be detected and produced one photon at a time. We usually don't notice this about light because the sun produces a ridiculous number of photons, about 10 to the 45 per second. That's 1 and 45 zeros. Most of these are emitted in the visible range, and only a small fraction are emitted in the highest energy bands, like the X-rays. If you take a picture of the moon in X-rays, you can actually count individual X-ray photons being reflected back from the sun by the moon's surface. So light sometimes behaves like a particle, a photon, but sometimes it behaves like something else entirely. If you now aim light at a wall with a slit, so there's a wall, there's a narrow slit, a narrow opening in that wall, and you believe that light acts as a particle, then you would expect that if light is aimed precisely at the slit, that light will go through and hit the detector wall at a point exactly in front of where that slit is. And if the light is not aimed at the slit and instead hits the wall, then it doesn't go through and is stopped at the first wall with the slit. So this is what you imagine would happen for a particle like beam. So if light was made of particles, this is what would happen. If you did this over and over and over again, you might expect that you would accumulate all of these photons directly in front of that slit. But when people did this experiment with a light source and a slit, a single slit, and a detector wall in front of it, What they actually saw was that the photons were distributed all along that wall, and in fact, they were distributed in a pattern that was very familiar from people who work with the physics of waves. This is a diffraction pattern. Waves, like the waves in water, for example, are diffracted when they reach a slit. If you have a tank that has ripple waves and you have an opening in the tank, then when those waves hit the tank, they form a circular wavefront that emits from that slit and serves circularly outwards. This is what you expect from something that behaves like a wave. You expect to see diffraction. But from these experiments, light also is diffracted through a narrow slit, just like the water waves. Further, two beams of light can cause interference patterns with each other. This was proved in a very famous experiment called Young's double slit experiment, where instead of just one slit in a wall, he made two narrow slits and aimed a beam of light at them again. Now again, if light consisted of particles traveling in straight lines, then either the particle goes through the slit or it doesn't, and when it does, it travels in a straight line. So at the detector wall, you would expect to see two locations where a lot of photons are detected and nothing along the rest of the wall. If light consists of waves, on the other hand, you would expect that at each one of those slits, new circular wavefronts are formed, and those wavefronts will interfere with each other and cause an interference pattern, like the one on the right-hand side of the screen, and in fact, that's what we observe for light. So, voila, light is a wave. Light behaves like a wave, therefore it must be a wave. But we saw it behave like a particle as well. We can detect individual photons. What's going on here? It's really both. The fact that light behaves like a wave and a particle, or the wave-particle duality of light, is one of the weirdest concepts in modern physics. It actually gets a lot worse, because quantum mechanics tells us that it's not only light that exhibits this type of behavior. Particles, regular particles like electrons or protons or atoms, also interfere with each other as if they were waves. So particles themselves have this wave-particle duality. And this was proved in this fascinating experiment that I really want to tell you a little bit about. It's essentially a version of Young's double slit experiment, where a beam of photons is aimed at a wall with two slits. But with added and increased technology, we can actually beam one photon at a time. So for hours, this experiment was run, where only one photon was beamed at a time towards this wall. You would expect that if only one photon is traveling between the whatever's generating the photon and the detector on the other side, then there's really nothing for it to interfere with, and therefore you would expect again to see those two neat little piles in front of the slits after you've accumulated, many photons over many hours. But instead, if you do this, and you do this repeatedly, one photon at a time, say every minute you send a different photon, and you record where that photon arrives at the detector, and then you send another one, and then you send another one, and you wait until the photons have accumulated enough so that you can detect a pattern, what you see is that same interference pattern that you saw before when you were essentially showering the experiment with photons. Now that's very strange, because if you think of the photon as a particle, and it's traveling through the slit, then it only travels through one slit, and why should it know about the presence of the other slit? And why should it know that it's supposed to interfere somehow with itself? These are really difficult and complex and infuriating and fascinating questions that quantum mechanics brings up, and that I really encourage you to learn more about in another course. In this course, we'll be a little bit more down to earth, and we'll use light in a utilitarian way, to try and find things out about astronomical objects. We'll often talk about light in terms of both its wave-like and its particle-like properties. Wave-like properties, things like wavelength and frequency, and particle-like properties, we'll talk about photons that are emitted and absorbed individually. Light is a form of electromagnetic radiation. When I say radiation, I don't mean the bad kind, but rather radiation is any sort of light that's emitted from a source. An electromagnetic wave is a disturbance of the electric and magnetic fields. Any wave has a wavelength, which we denote by the Greek letter lambda. We define the wavelength of a wave as the distance between two successive crests or troughs. It's therefore defined in units of distance, like a wavelength can be 1 meter, or 1 millimeter, or 1 nanometer, or 1 kilometer. You get the idea. The frequency of the wave is actually how many wavelengths pass through one specific point within 1 second. So it's measured in units of inverse time, 5 per second, or 10 per second. Another important thing to note is that the energy of a wave depends on its frequency or its wavelength. You can think of this easily if you imagine someone holding a jump rope and how much more energy is required to wiggle it fast so that there's lots of little wavelengths inside, rather than to wiggle it slowly and gently so that the number of wavelengths is smaller. The color of light that you observe depends on the wavelength, lambda. The violet end of the spectrum has a very short wavelength, only 400 nanometers. The wavelength increases progressively through indigo, blue, green, yellow, orange, and red. At the red end of the spectrum, the wavelength is the longest, at 700 nanometers. Conversely, the energy is at its lowest on the red side of the spectrum with the longest wavelength, and it increases towards the violet. It's important to note that these wavelengths that we're talking about, these distances, 1 nanometer, are exceedingly small. 1 nanometer is 10 to the minus 9 meters. That's only the size of an atom. Another thing worth defining is what a spectrum is. A spectrum is a graph that tells you how much light there is at each wavelength. If you were to take light from a source and use a diffraction grating or a prism or even a raindrop to disperse it into its constituent colors, you might obtain an image that looks like what's on the top of the figure here. You see the red, orange, yellow, green, blue, indigo, violet of the rainbow. But you also see some dark lines in that image where there's no light coming through at all. So if you were going to plot this in a graph where the wavelength is at the bottom, then you would start by noting that on the right-hand side you have violet at 400 nanometers, and on the left-hand side you have red color at 700 nanometers, so that the wavelength in fact increases towards the left rather than towards the right, as is usually the case. And now you can plot what that intensity of light is as a function of color or wavelength. And we notice that those black lines in the image are now translated into dips in that intensity spectrum. So when there's a black line, that means that no color is coming through, so the intensity is low. That was sort of obvious from just looking at the image. At those points, at those specific colors, there is no light. On the other hand, it's really hard from looking at that top image which colors are the brightest, because our eyes identify colors or react to colors in different ways. So you really need to make a measurement. And by measuring how much of each color you see in a graph like this, you can see that in fact there is more green and yellow than there was red and blue in this particular spectrum. To recap, the energy of light depends on its wavelength. The longer the wavelength, the lower the energy. So blue light, which has a short wavelength and a high frequency, has high energy. And red light, which has a long wavelength and a low frequency, has low energy. This is the opposite of what our faucets have taught us to expect, where hot is red and cold is blue. Physically, blue colors are much hotter than red colors, more energetic than red colors. We denote the speed of light in a vacuum by the letter c, because the speed of light is constant and is equal to 299,792,458 meters per second. For a long time, no one knew if light was infinite or finite in speed. It was just too fast to measure. The first measurement for the speed of light actually came from the transit of Io, one of Jupiter's moons. You might recognize this figure on the bottom right as being quite similar to the one you guys made in your labs. Here we're following the orbits of the 4 Galilean moons of Jupiter throughout their orbits. This graph follows those moons over 20 days. In our lab, I only had you track the motions for a little over 2 days, so only this section of the graph. And you'll see that it looks a lot like what you obtained. You were able to follow Io throughout its entire orbit, Europa through not quite half, Ganymede through not quite a quarter, and Callisto, well, really only a fraction of the orbit, a small fraction of the orbit. You can see here that the orbit of Io is approximately 1.75 Earth days, or 42 hours. You could have measured that from your observations. And at this time, people were really excited about the idea of using the orbits of the moons of Jupiter as sort of celestial clocks, because the orbits are extremely regular. They always happen at the same period. So there was a lot of work towards really pinning down what that orbital period was. And there was a Dutch astronomer called Ole Romer who was trying to do just that. He was taking observations, essentially every 2 days, a little bit under 2 days, sort of looking at Io as it's orbiting around Jupiter, and particularly carefully looking at the times when it comes out from under Jupiter. If you remember back to your lab, or maybe your observations during our star party, that Io, as it's orbiting around Jupiter, occasionally goes behind Jupiter, sometimes it goes in front of Jupiter, and it does this once per orbit. So you can follow Jupiter in its orbit and essentially measure what the time is every time that it just either dips under Jupiter or emerges from behind Jupiter. And you can measure that time very precisely, and thus, locate a particular position in the orbit that you're always looking at, and determine whether that orbital period is constant. So that's what Ole Romer was doing, and what he found was that, very surprisingly, the orbital periods were changing according to how close Earth was from Jupiter. Now, this really made no sense to him, because there's no reason why the orbital period of a moon around Jupiter should know anything about where the Earth is with relation to Jupiter. So it was very confusing for a long time, until he finally had this brilliant insight, which is that it actually takes light longer to reach us from Jupiter when we're on the other side of our orbit, so when we're further away from Jupiter, and that's what was causing the delay in the transit times. So if you look at this figure, the larger circle is the orbit of Jupiter, and the smaller circle is the orbit of the Earth. The Sun is at the center of both. Now the Earth goes once around its orbit every year, and Jupiter moves much more slowly in its orbit. It takes almost 12 Earth years to go around once. So if we start at time 1, where Earth and Jupiter are on the same side of their orbits, then they're at their closest position, and the distance between them is about 4 astronomical units. Remember, 1 astronomical unit is the distance between the Earth and the Sun, about 93 million miles. At a time later, time 2, the Earth, and this is about 6 months later, the Earth has moved to the opposite side of its orbit. Jupiter has only moved a little bit along its orbit, so now we're at one of the furthest positions from Jupiter that we can be. In this case, the distance between Earth and Jupiter is closer to 6 astronomical units. Convince yourself that that's true by looking at the figure. So that means that between positions 1 and positions 2, there's a difference of 2 astronomical units. If you remember from last lecture, it takes light 8 minutes to traverse that distance, i.e. it takes the sunlight 8 minutes to reach us from the sun. If we're going to traverse twice the distance, or 2 AU, it's going to take light 16 minutes to traverse it. So that when the Earth is on the opposite side of its orbit, light is actually taking 16 minutes longer to reach us from Jupiter than it used to when we were on the same side. And that was exactly the types of delays that Ole Romer was seeing in his observations. From the amount of delay, he was able to predict what the speed of light was. Now, speed, as you know, is equal to distance traveled over the time it takes. And so when we think about the speed of a wave, we can think about the distance between the peaks divided by the time between the peaks. Now, the distance between the peaks is just the wavelength of the wave, and the time between the peaks is just the inverse of the frequency. So if we substitute that in, we can see that the speed of light, c, is equal to lambda, the wavelength, times nu, the frequency. Or, if you want to solve for lambda, you can say that the wavelength is equal to the speed of light over the frequency, or conversely, that the frequency is equal to the speed of light over the wavelength. Now, we always know what the speed of light is because it's constant. So we can, if we know the wavelength, you can calculate the frequency and vice versa. In a vacuum, light will travel at the same speed in a straight line forever. The real universe is not a vacuum, thank God. And so light travels in a straight line until it encounters matter and interacts with it. In these interactions, many things can happen to light. It can be transmitted, or reflected, or absorbed. It can be refracted and polarized and diffracted and scattered. We've talked about pretty much all of these already, but let's review what we mean by each of these terms. When light is reflected, it encounters a surface and is perfectly reflected back. The angle of incidence is the same as the angle of reflection. This is what happens when you look yourself in the mirror. The perfectly shiny, smooth surface of the mirror is reflecting almost all the light back. Some light, instead of being reflected, is transmitted through the object. This happens for see-through objects like cellophane or glass or water, where the light travels through the medium without being reflected. Sometimes light will strike a surface and it'll be absorbed. When that happens, often the light is absorbed by the molecules, with its energy being converted into molecular motion. When molecules absorb energy from light, they absorb it into their vibrational motions, and so they start vibrating faster. When molecules vibrate faster, their temperature goes up. That's the definition of temperature, is one of how much motion there is in the molecules that make any object. So if light strikes an object, the molecules in the object absorb the light, and they start moving faster, and so the temperature goes up. This is what happens when you step outside on a sunny day and your body feels warm. Sunlight is striking your skin and is being absorbed, and the molecules in your skin are literally moving a little bit faster because of this, and that's what you perceive as heat. That's what your brain interprets as heat. Same thing was happening when we did our solar brightness lab the other day. You were able to use your hand as a rudimentary photometer, because when you put your hand close to the bulb and the light and the photons from the bulb are striking the hand, they are being absorbed by the molecules in your skin, and those molecules are moving faster, and that's what you perceive as a higher temperature. Most of the time, light doesn't just get reflected, or just get transmitted, or just get absorbed. It does all three. And the relative amounts of reflection, absorption, and transmission will depend on what that material is composed of, but also on the wavelength of the incident light. We could think of this again in terms of white light striking a surface, but we know that white light is actually just a combination of all different types of light: red, orange, yellow, green, blue, indigo, violet. All of those colors are striking the surface at the same time, and in this particular surface, pretty much all of them will be absorbed except for green. Green is reflected back. Red and blue and yellow and indigo are being absorbed. What that looks like to us is a green object, because it reflects green and absorbs everything else. Now, I want to talk about refraction. Refraction is what happens when light moves through a medium. And when light moves through a medium, like water, glass, or air, its speed goes down. Its speed becomes less than c, and the speed in that medium will depend on the wavelength of light. When light is transmitted through the glass in a prism or the water in a raindrop, as the speed slows down, the angle at which the light is traveling changes. Instead of going in a straight line, the light will bend, the most for the shorter wavelengths, and it will bend the least for the longer wavelengths. So the red light bends the least, and the blue light bends the most. That's because the red light is slowed down the least, and the change in speed is related to the change in angle. This is what happens in a prism, and this is also what happens in a raindrop, in a spherical raindrop after a heavy rain when the sunlight comes out. The white light strikes the spherical raindrop, and it gets refracted inside of that spherical surface. But the angle that it's refracted at is slightly different for the red light and the blue light. And so by the time that they exit that spherical drop, there's a difference between where the red light and where the blue light is. And that difference is called dispersion. We've dispersed the light into its separate components. Rainbows are fascinating physical objects, and I really encourage you next time that you see one to really stop and observe it, because it has these amazing qualities and characteristics that you can start to understand by applying the physics of light and the physics of light refraction. For example, in this rainbow over the Grand Canyon, you notice that, first of all, the colors are ordered from blue on the inside to red on the outside, but also that the inside of the rainbow, under the blue, is much, much brighter than the outside of the rainbow over the red, so that the inside of the rainbow seems to be sort of a bright whitish color. That's something you can easily understand by applying simple laws of refraction. In this case, it's a little bit more obvious, the difference between the brightness inside the rainbow and outside. Another rainbow phenomenon that's become particularly popular in recent years is the double rainbow. Double rainbows are not that rare. You can see them often in the Tucson sky, especially during monsoon season. When you have a double rainbow, one of the things that is really exciting to notice is that the colors are actually reversed in the second rainbow. So the first rainbow goes from blue to red, but the second rainbow starts at red and goes to blue. You can also in this picture again see the difference between the light inside the rainbow and the brightness outside. The location, the ordering of the colors, the number of other rainbows that you can see are all dictated by the laws of physics and the laws of light refraction. And with a little more time, or during an introductory optics class, you would be able to understand exactly why rainbows look the way they do, what size they have, and why you can only ever see them when you're facing away from the sun towards rain. One last thing before we go. Light, when it encounters small particles, can be deflected in random directions as it bounces off the molecules. This is the process of light scattering. Again, like other processes we've seen so far, this process is wavelength dependent. The shorter wavelengths are more frequently scattered than the long ones. If you look at the graph in the lower right, you'll see, as a function of wavelength of color, the percentage of light that is scattered from direct sunlight. That means that for each individual photon of light, they're not all scattered, but the percentage of photons that will be scattered is much higher if the photon is blue than if the photon is red. That's what makes the sky blue, since the blue photons are scattered so much more often by the atmosphere. And it's also what makes sunsets red, because if you think about it, when the sun is setting, it's going through so much more atmosphere, and the scattering has become so much more intense, that all of the blue light has been scattered out of the path of the sun, and all that remains is a red-yellow sun. One last thing before we go. If you look at this figure, it's showing a constant increase of the scattering efficiency as a function of wavelengths, so that the smaller wavelengths are scattered more frequently. So it's telling you that it's not the blue wavelengths that are scattered the most, but it's in fact even shorter wavelengths like violet and indigo. So why is the sky blue and not violet if the violet lights are being even more scattered than the blue ones? The reason for that is actually back in human vision and human physiology. Those cones that we talked about at the beginning of this lecture, they're really not very sensitive to the violet end of the spectrum. You can go back and check it out after we've finished here. But the sensitivity at those wavelengths is really much smaller. So even though the sky really is violet, we as humans perceive it to be a nice baby blue.